Maria and David and everyone for the invitation to give this talk. I just wish I could be there in person in ICFO or Munich, whichever place it was meant to be held the workshop at the school. So I'm going to tell you indeed about this field of moiré quantum matter and the magic of moiré quantum matter. It is a relatively new field, okay, and something that a lot of us in condensed matter are interested by. I think also it has many things to overlap with the field of ultra cold atoms in optical lattices, which I think many of you do. Okay, now I'm going to start from a little bit more of a general point of view, and this is to say that among the most fascinating states of matter that we have in the universe are those where strong interactions between the individual constituents play a dominant role. Okay, so this is something that happens, for example, at the quark room, in the quark room plasma state. Okay, this is some state of matter that happens a few hundreds of nanoseconds or microseconds until after the Big Bang, and that we can recreate nowadays in heavy ion collisions in accelerators such as those at Brookhaven National Laboratory. The different phases of nuclear matter in neutron stars also are strongly correlated. This is a picture of a neutron star by the Chandra X-ray Observatory. And if you go to Wikipedia and you look at the nuclear matter in neutron stars, you will see that there are various different phases, that have very interesting names. They call them nuclear pastas. So they have the lasagna phase, the bucatini phase, etc. As you saw, the astrophysicists are very creative in naming things. And then perhaps a bit closer to my heart, the different topological states of matter are often very strongly correlated too. So for example, if you subject a two-dimensional electron gas to a perpendicular magnetic field, then you can enter the fractional quantum Hall regime where your quasi-particles there have fractional charge, and they also have very interesting topological properties. Now, if we zoom in a bit more into the field of strongly correlated quantum materials, these are, there are many classes of materials that are like that. And in particular, one of the most studied one are the high temperature couplet superconductors, where, for example, in this phase diagram of temperature versus doping, we have a variety of phases, few of which we have a detailed understanding of even to this day. Okay? Now, that lack, the part of the reason why this happens is that strongly interacting systems are very hard to solve theoretically. Okay, to take the couplets, for example, the high temperature couplet superconductors, all of the action takes place in these copper oxygen planes, where at the stoichiometric parent compound has one electron per unit cell, per copper atom. Okay, and these are stuck in their positions due to the very strong Coulomb repulsion between these electrons. Now, an interesting game happens when you dope with holes, when you remove some of these electrons. Okay, now because there are some empty sites, these electrons can tunnel from side to side, and they have to do that in a correlated fashion, so different sites get emptied and occupied. Yeah, and that interesting correlated motion of all of the electrons leads to interesting things. It is believed to lead to interesting things such as high temperature couplet superconductivity. Okay, now we go from this correlated mode insulator type of behavior to superconductor. The basic model that is believed to capture the essence of this behavior is the Hubbard model, okay, which takes into account the strong Coulomb repulsion, to occupy a site with two electrons, and that it allows you also to tunnel between sites. But we don't know how to solve this problem theoretically, and therefore we do not know truly to what extent this Hubbard model really leads to the variety of phases that we can observe in systems such as high temperature couplet superconductors. So these difficulties have in theoretically solving, despite decades of work, of theory work on the Hubbard model and related models, has led to different platforms to investigate the physics of strongly interacting systems. Okay, and traditionally we've had two platforms: quantum materials themselves with lattice scales of the order of a few angstroms. Okay, and more recently, ultra cold atoms in optical lattices for the past 2 decades or so. Now, the lattice scale in quantum materials of the order of a few angstroms. For ultra-cold atoms is of the order of a micron, okay? And what my group, discovered a few years ago, back in 2018, is that we have now a new platform. It's called moiré quantum matter, okay? And the first example was magic angle graphene, but there are many examples by now, where this length scale, the moiré length scale, is of the order of 10 nanometers, so it's nicely about a couple of orders of magnitude from either of these other traditional platforms. Now, associated with these length scales are temperature scales. In quantum materials, typical temperature or energy scales are of order 100 to 1000 Kelvin. In cold atoms, 0.1 to 1 nanokelvin. In moiré quantum matter, these are typically of the order of 1 to 10 Kelvin, maybe 1 to 100 Kelvin. Yeah? So this, this moiré quantum matter is a new platform which is complementary to these other platforms. We have more control and tunability than in quantum materials. We do not have as much control and tunability as the cold atoms in optical lattices, but we so far have a bit of a better access to the phase diagram, as I will show you, okay? So the thing that has possibilitated this moiré quantum matter is something that had no history in the no precedent in the history of material science, which was the fact that we can put two 2D crystalline lattices on top of each other and choose any angle of rotation that we want between them, okay? That is something that you could not do when you grow thermodynamically crystals. It's not something that you can do by growing out of equilibrium semiconductor or metallic heterostructures. It's something that could only be done with the advent of 2D materials, okay? And that's something, that we're exploiting at the moment, and a large fraction of the community is doing. In fact, for materials, for 2D crystalline materials which are different, you don't even need to twist. Just aligning them on top of each other, due to the lattice constant difference between these two materials, you can have moiré patterns where you can have similar physics in some cases. So with this introduction, this is what I want to tell you about today. I'm going to start by telling you about magic angle graphene, about graphene, magic angle graphene, and moiré quantum matter, okay? And what are the recent developments that have happened since our discovery back in 2018. Then I want to tell you about the next generation moiré quantum matter, something that I call moiré magic 3.0, okay? Which has to do with the recent discovery of a new moiré superconductor, magic angle trilayer graphene, or magic angle twisted trilayer graphene, okay? I will tell you about the system. It's much more highly tunable than the bilayer case. It realizes ultra strong coupling superconductivity. And I'll tell you at the end about an unexpected surprise, which has to do with the behavior of the system in a magnetic field. And then I'll end with a little bit of an outlook of things that are happening in related fields and things that, where I think things will move to. Okay, so let's start with graphene, magic and graphene, and moiré quantum matter. So let's start with graphene. Okay? So graphene is a honeycomb of carbon atoms. Okay? All of these atoms are, from the chemical point of view, identical, carbon. Okay, but from the crystallographic point of view, it turns out that we need two inequivalent sites here. You need a two atom basis and two unit vectors to style a honeycomb into dimensions, okay? So we call those two sublattices A and B, or red and green balls in this drawing. Now, in a simple quantum mechanical model, you can calculate the electronic structure of graphene, and it turns out, here it is, energy versus momentum in the X and Y direction. And it's a very famous electronic structure because it's very unusual. Near the Fermi energy, near charge neutrality, you have this linear energy momentum dispersion, which is more characteristic of things like photons, right? But usually you have quadratic energy momentum dispersions in solid state systems, but in graphene, because of its symmetry properties, you have this linear energy momentum dispersion. Okay? Now, this has led to all kinds of analogies with ultra relativistic particles and etc. And indeed, the equation that in which you can formalize this linear energy momentum dispersion is this Hamiltonian equation, okay, where the energy is proportional to linear to the momentum. This is nothing else but the Dirac equation in 2 dimension for massless particles, okay? Now, in the usual Dirac equation, this is the only equation I'm going to have the entire talk, I think, so don't worry, or maybe I have one more. In the usual Dirac equation, this is a spinor, which tells you whether the electron spin is up or down. In the case of graphene, this is a pseudo-spinor, which tells you whether the weight of the electron wave function is on the A type of lattice or on the B type of lattice, okay? Now, the only other thing I want you to know about graphene is the fact that we have two of these double Dirac cones, okay? We call them valleys, the K and the K prime valleys. They're degenerate in energy. So what we say is that in graphene, electrons have 4 degrees of freedom, you know, spin up, spin down, valley K prime, okay? That number 4 will appear sometimes in the talk, so it's good if you remember it. Now, what happens if you put graphene on top of graphene, okay? Now, if you put graphene on top of graphene and you twist it, okay, you form a moiré pattern in real space, okay? Where the moiré wavelength, which is the distance between the soccer balls here in this animation, okay, it's roughly inversely proportional to the twist angle, okay? And it can go all the way to infinity for small twist angles because these are identical lattices, okay? Now, let me stop this thing. So this is what happens in real space, what happens in momentum space, and what happens therefore to the electronic structure, okay? So let me start from a twist angle that is small so that, you know, the separation between the Dirac cones in momentum space is already proportional to the angle. So again, what do these two Dirac cones mean? These two Dirac cones are the Dirac cones from layer, you know, electrons in graphene layer 1, and the other Dirac cone is the Dirac cone from electrons in graphene layer number 2. Okay? When you rotate in real space, the reciprocal spaces also rotate, and the Dirac cones are a little bit separated. Okay. Now, this would be the situation that you would have if the electrons in one graphene sheet did not know about the other graphene sheet. Okay, the electronic structures, they would just interpenetrate each other. Okay. However, in reality, when we put graphene on top of graphene, these two graphene sheets are just 3 angstroms apart. So the electrons can tunnel, you know, between the two sheets. They're very much aware that the other graphene sheet exists. So they can form bonding anti-bonding states, okay, which open a gap here at the point where you have that intersection, okay? This interlayer tunneling leads to the opening of a gap, and in particular, it pushes, the bonding state gets pushed down in energy a little bit, okay? Now, this is very similar to hydrogen, you know, to bonding anti-bonding states in a hydrogen molecule, but what we have now is a giant graphene molecule, okay? Now, the situation is what happens when this interlayer tunneling energy is repulsion is smaller than the energy of that crossing point. But as you decrease the twist angle, okay, these two Dirac points come closer and closer and closer. At 0 degrees, they would be on top of each other, okay? So they come closer and closer and closer, and this bonding state, this bonding band gets pushed down to lower and lower energies until it reaches 0, okay? That condition, okay, when the interlayer tunneling is of the same order as the energy of that crossing point is, you know, when that condition happens, we say that a flat band condition has been reached, okay? And that occurs at the magic angle, which was theoretically predicted to be 1.1 degrees for graphene on top of graphene, okay? So this was, you know, theoretical predictions by Eric Morel and the BCS McDonald predicted these flat bands at this magic angle. And there was actually a slightly earlier experimental work, single particle physics experimental work using scanner and tunnel microscopy, where they saw that a Van Hoff singularity, which occurs here, a divergence in the density of states, goes to 0 as you go towards this angle, okay? So there was already interesting work back then, experimentally. Now, this, you know, this thing that I showed you before is a cartoon, okay? This is an actual calculation of the energy versus momentum, okay, for magic angle twisted by layer graphene. These are those flat bands that occur, okay? As you can see, they're not exactly flat. There is a little bit of dispersion, but they're much, much flatter, okay, than the original graphene dispersion. Now, these are the remote or other, you know, remote moiré mini bands. These are the ones where the interesting physics primarily takes place. Now, flat in momentum space, okay, if you want to think now, okay, let me put electrons in those flat bands. where do they like to go in real space? Yeah? Now, to go from momentum space to real space, you have to do a Fourier transform. So flat in momentum space means highly localized in real space, okay? So if you calculate when you put electrons in these flat bands, where do they like to sit? Okay, it turns out they like to sit locally in regions where the two, the two carbon, the two graphene sheets locally look like all the carbon atoms are on top of each other. These are regions of AA stacking locally. Okay, these regions are tunnel coupled by regions where, due to the twist angle, the registry of the carbon atoms changes, and locally those regions are of AB and BA type of stacking. So schematically from the top, this is how magic angle graphene looks like. Okay, you have a moiré pattern with regions where you have AA stacking where electrons like to sit, okay, and regions with AB and BA domains where electrons do not like to sit. Okay, in a slightly more realistic schematic, okay, magic angle graphene has these regions of AA stacking where electrons like to sit. Those regions are spaced by about 13 nanometers, okay? And this is what's going to be, the equivalent of, a Fermi-Hubbard lattice in cold atom systems, okay? It's a triangular Fermi-Hubbard lattice, triangular in quotes because in reality, it's a honeycomb lattice, honeycomb structure because the AB and BA domains are not identical. And there's something that endows the lattice with special topological properties which differ from the usual Hubbard lattices that are studied in cold atom systems. Now, what we discovered, my group back in 2018 is that if you put the chemical potential, the Fermi energy of your system in these flat bands, you have interesting correlated insulated states when you feel a certain number of electrons per molar unit cell, and when you dope away from that filling factor, then you have superconductivity, okay? This type of behavior is something that occurs only in a relatively narrow angular range around this magic angle, okay? Let's say plus minus 1.1 plus minus 0.1 or plus minus 0.2 degrees is when this type of physics happens. So it's intimately connected to the presence of those flat bands for magic angle graphene. Now, magic angle twisted bilayer graphene is an electrically tunable superconductor, okay? So in our devices, we have the magic angle graphene, and we have a nearby metallic plate, a parallel, so that we can make a parallel plate capacitor, and by applying a voltage, change the charge on the plates of your capacitor. And one of the plates is the magic angle graphene, okay? So one of the interesting things about the system is that, you have a correlated insulated state when you put, in this case, 2 holes per molar unit cell, okay? I'll mention a bit more about this later. And then if you add extra holes, you have a superconducting dome. If you have electrons, okay, so you remove a few holes or you add electrons, you have another superconducting dome for electron doping, okay? Now, when my students showed me this for the first time, I was immediately fascinated because of the hundreds of times that I've seen, phase diagrams such as this, okay? Now, this is the phase diagram for high temperature couplet superconductors, okay? Let me flip this axis so that they correspond to electron hole doping similar to us. In high temperature couplet superconductors, 0 doping means 1 electron per unit cell, and you have a MOT insulator, a correlated insulator. If you add holes, you have a big superconducting dome. If you add electrons, you have a smaller superconducting dome. In magic angle graphene, this correlated insulated state corresponds to 2 holes per molar unit cell. If you add extra holes, you have a superconducting dome. If you add extra electrons, you have another superconducting dome, okay? Now, a big difference between these is that this is a theoretical phase diagram, okay? In order to populate this with experimental points, you have to grow hundreds of crystals with different doping, often with different material classes, because not all crystals can be grown, for electron doping, for hole doping, whereas this is all realized in a single device, in a single cool down, with a single disordered realization, and where I can tune electrically from here to here in a few seconds, okay? So that's something that obviously attracted a lot of attention. Now, so we discovered this thing back in, we announced it at the APS March meeting in 2018, and then, the theory tsunami came, okay? So people started to look at, this is just a short list of the first papers that appeared within a few weeks of us posting our discovery. Everybody was very interested in learning about the origin of the correlated insulated states and what is superconducting order parameter. All kinds of theoretical predictions have been made. The first one was a paper by Senke Xu and Leon Valens saying that this is a triangular lattice with a D plus IT Kähler topological superconducting state. Then people realize it's not exactly a triangular lattice, it's a honeycomb topology. All kinds of order parameters have been predicted with all letters of the alphabet, S, P, D, F, S plus P plus D, you name it, okay? So as this was a bit of a surprise for me, but in this, in the theoretical community in strongly correlated physics, there is a lot of disagreement, okay? And that's something which, coming from graphene was a little bit new to me. And there's some interesting, the second theory paper posted was by Gregory Bolovic, who told us that, he had predicted all of this, and he told us how to get to room temperature superconductivity by stacking more and more layers, okay? So it's an interesting paper. I encourage you to have a look at it, and who knows, maybe such a thing might happen one day. Now, in addition to, theory tsunami, also the popular press started to be interested in this. So lots of papers and interesting stories appeared with very cool pictures. This is one of my favorites. I wish I knew how to make this type of pictures myself. And I call this the rise of moiré quantum matter. Yeah. Now let me tell you a little bit about what are the experimental developments that have happened since we our paper was, we announced the results in March. The paper was officially published in April 2018. So the first thing that has happened is that we have reproduced our own results many times, okay? Now, that's, that doesn't always happen, so it's good when it happens, okay, that you're able to reproduce yourself, okay? So since then, we have, many more devices. We're starting to look at what's the critical temperature at optimal doping as a function of twist angle. So we have a superconducting dome, but in a new parameter, twist angle, okay? And this is something that, us and many other groups are doing. The second thing is that, even better that you reproducing your own results is when other groups completely independently reproduce your results. And only then it becomes true science, okay? And since our discovery, the first two groups to reproduce our results was the group of Corey Dean, a collaboration between the groups of Corey Dean and Andrea Young, where not only they reproduced our results, but they were able to tune superconductivity by applying pressure. So they extended our results in very interesting directions. And then the second group was the group of Dmitry Efetov at ICFO, where they showed that in one device in particular, they could show additional superconducting, domes, so the phase diagram could become richer. Yeah? By now, superconductivity is a very robust phenomenon reproduced by and extended by many groups, about a dozen now experimental groups or so at various places, all over the world. So this is something that is very firmly established now. Now, we have discovered other correlated systems, for example, magic angle twisted bilayer graphene, that was the second twisted, twistronic systems to be discovered. This is now, you take 2 layers of graphene with the usual stacking that you have in graphite. It's called Bernal stacking. So 0 degrees between the 2 layers. You have another 2 layers, again with 0 degrees. And now you twist them pairwise. Okay, so you have 4 layers in total. And you twist the upper 2 with respect to the bottom 2 by the magic angle. That's called magic angle twisted bilayer graphene. It's not a superconducting system, but it's an interesting correlated system with interesting magnetic properties. Okay, and that was the second system to be discovered. We have, the community has also been doing scanning probe microscopy studies, scanning tunneling microscopy, scanning nanosquid, plenty of such studies. Let me tell you about one in particular, which I think has given us a lot of insight. Okay, the phase diagram of magic angle twisted bilayer graphene initially was mostly determined by global transport, electronic transport measurements. That was our study at Columbia and Santa Barbara, the study at ICFO, okay? And what we saw, okay, this is schematic, it's twist angle dependent and it's evolving fast, but to 0th order, what we saw is that in a plot of temperature versus filling factor nu. Okay, what is this filling factor? This filling factor is telling us how many electrons or how many holes are we putting per moiré unit cell, okay, electrically. How many electrons or holes are we doping per moiré unit cell in these flat bands, okay? From charge neutrality, which is 0, you can add up to 4 electrons per moiré unit cell, then you reach the top of this conduction band. Because you reach the top of the conduction band, afterwards you have this, at 4 electrons per moiré unit cell, your chemical potential is here in a single particle band insulator, so you have band insulator state, okay, 0 conductance. If from charge neutrality, you remove 4 electrons or you add 4 holes per moiré unit cell, you reach the bottom of the valence band here. So your chemical potential goes here, where you have, again, a single particle band insulator, and that's the behavior that we see. Remember, I told you that electrons in graphene have this 4-fold degeneracy, spin up, spin down, valley K, valley prime. That's why you go from +4 to -4, okay? Essentially here. You also have 2 layers. So in total, you can put 8 electrons per moiré unit cell in these flat bands. Now, the interesting thing that we saw back in 2018 is that at 2 electrons and 2 holes per moiré unit cell, you have a correlated insulator state. Since then, other studies, both by our groups and by other groups, have seen that quite often you also see correlated insulator states at 3 electrons, sometimes at 3 holes per moiré unit cell. And you see also correlated states, not insulators, but correlated semi-metallic states at 1 electron, and sometimes at 1 hole per moiré unit cell, okay? And you can have even an insulator state also at 0 sometimes. Now, as we dope away from these correlated insulator states, you have superconducting domes. The most prominent is this one, when you dope holes, extra holes around the correlated insulator state at 2 holes per moiré unit cell. But sometimes you also have this one, you also have this one, you also have this one, and occasionally there are a few others, okay? So this is the phase diagram from transport measurements. Now, last year we started to do thermodynamic measurements, okay? In particular, compressibility measurements. Your chemical potential is mu. The derivative of the density with chemical potential is called compressibility, and d mu dn is the inverse compressibility. D mu dn tells you how is your chemical potential changing when you add charge to your system, okay? And in an interesting, collaborative work with my colleague Shah Halilani at the Weizmann Institute, and very similar results were obtained by the group of Ali Yazdani using scanning and tunneling microscopy. What we were able to do is the following. We took a scanning single electron transistor, is a very sensitive, electric field, voltage meter, okay? And we were able to scan on top of magic angle graphene as a function of filling factor as we were changing the charge density. And what we saw in the inverse compressibility, the mu dn, is this set of, this sawtooth type of behavior and these peaks that occur close to all of these integers, okay? Let me zoom in into one of these here, okay? Now, the description of this is a little bit complicated. The only message that I want you to walk away with is the fact that something happens near each integer, and that something that is happening, okay, to 0th order can be understood as the following. When you are at charge neutrality, you have these 4 Dirac cones, these 4 flavors that you want to fill, okay? Spin up, spin down, valley K prime, in the simplest case. As you add charge to your system from charge neutrality, all of these 4 flavors start to get filled at the same time. However, near an integer, okay, so when you have put about 1/4 of an electron per moiré unit cell in each of these flavors, so a total of 1, the system decides to spontaneously flavor polarize, sends all the charge carriers to occupy 1 flavor and empties the other 3 charge carriers, okay? And then you start again. You now fill the other 3 remaining flavors, close to 2, okay? The system spontaneously polarizes into 2 of these flavors fully occupied, the other 2 fully empty, and you do this again, okay? That thing is called a cascade of phase transitions, okay? And it can be understood as, due to Coulomb interactions, the system is energetically favorable for the system to polarize into 1 flavor and empty the other flavors. And that gives you this sawtooth behavior theoretically. Okay, so that's all I want you to know, for now. Okay, so in addition to all of this physics that I just described, a very interesting development that happened also is that ferromagnetism, anomalous Hall, and quantum anomalous Hall physics was discovered in these systems, which meant that topology plays a crucial role in the physics of magic angle twisted Pauli graphene and related systems. Okay, so in fact, this correlated moiré heterostructures has meant, this field of moiré quantum matter has meant the merging of several modern condensed matter physics communities. Okay, on one hand, you have the 2D van der Waals materials and heterostructures community. On the other hand, the strongly correlated materials, like people that worked on cuprates, and the people that worked on quantum Hall, topological insulators, etc. Okay, all of these come together in this field of correlated moiré heterostructures. Now, a little bit after our discovery, together with our theory collaborators, we predicted that indeed nearly flat Chern bands would form in these moiré superlattices in all kinds of moiré superlattices. So the importance of topology was predicted theoretically first, and then experimentally, the group of David Goldhaber-Gordon showed in magic angle graphene aligned to hexagonal boron nitride, they showed this large anomalous Hall effect, meaning that there was ferromagnetism. Okay, and then 6 months later, the group of Andrea Young showed this quantized anomalous Hall effect, okay, which brought, again, topology front and center. Similar experiments were done in a different moiré system, ABC Trilayer graphene on hexagonal boron nitride, okay? And this has now grown into, many theory groups and experimental groups are working on these aspects too. Now, let me tell you about the next generation, okay? Moiré quantum matter, which was recently discovered. So just last month, my group and the group of Philip Kim at Harvard University, we both published on the same week. We published in Nature, they published in Science, this new system, magic angle twisted trilayer graphene, okay, which is a new robust superconductor, much more highly tunable and much more interesting than the magic angle bilayer itself. Okay, so the system is, in particular, mirror-symmetric magic angle twisted trilayer graphene. What do I mean by that? Okay, it's 3 layers of graphene instead of 2. Okay, the bottom and the top layer are exactly aligned to each other. Okay, 0 degrees angle with respect to each other, and all of the atoms on top of each other exactly aligned. And the middle layer is rotated by an angle theta. Okay, so as you go from bottom to top, you rotate one layer by an angle minus theta, and then the next layer by theta with respect to the middle, so the bottom and the top are aligned. Okay, this is a geometry that was first proposed by Eslam Khalaf and the group at Harvard University and the group of Ashwin Vishwanath, and it's called A twisted A stacking. Okay, because all of the atoms in the bottom and the top layer are on top of each other, and the middle one is the one that is twisted. Okay, now, related work on mirror-symmetric magic angle twisted trilayer graphene has been done by several groups, and also on twisted trilayer and multi-layer systems. By now, there are many dozens of papers on systems beyond 2 layers. Okay. Now, one thing that is very interesting is that the electronic structure of the system, you can think of these 3 layers, okay, as magic angle bilayer graphene plus monolayer graphene. Okay. Turns out there is a linear combination of the orbitals in these 3 layers. The symmetric one that gives you a magic angle twisted bilayer graphene-like system with, interesting, a square root of 2 larger interlayer tunneling. And then the anti-symmetric combination gives you monolayer graphene-like band structure, okay? Now, because of this square root of 2, remember I told you earlier that the interlayer tunneling determines the magic angle, okay? Because of this square root of 2, the magic angle for twisted trilayer graphene happens to be the one for the twisted bilayer graphene times square root of 2. Okay, so it's 1.1 degree times square root of 2, 1.56 degrees. That means that the moiré wavelength, okay, because the angle is a little bit larger, the moiré wavelength is now smaller. It's about 9 nanometers instead of 13 nanometers, as I told you earlier, for the bilayer case. Okay, and one can calculate the electronic structure in the system. Okay, and as you can see, it has these flat bands, these orange bands, which are flat bands, which look, very reminiscent of the magic angle twisted bilayer graphene-like. And then you have, on top of that, a massless Dirac cone similar to graphene. These 2 bands coexist, okay? This is the electronic structure at 0 displacement field, okay? It turns out that in one of our devices, we have bottom and top metallic electrodes, so that we can, by applying voltages, we can not only change the charge density, but we can also apply a transverse electric field in the perpendicular direction, okay? That transverse electric field breaks the mirror symmetry of the system and leads to a coupling of this flat band and this massless Dirac band. Okay, at finite displacement field, they get hybridized. So we have a knob now with which we can tune the electronic structure of this system, which is something that we could not do with the bilayer case. Okay? Now, let me show you that this system is a new robust moiré superconductor. Okay, you have zero resistance in the resistance versus temperature curves. You can determine the Berezovsky-Koster-Lithaus transition temperature, which is about 2.3 Kelvin for this device. The TC 50% is about 2.9 Kelvin. Okay. The system has flat voltage current characteristics with sharp switching. You can do temperature dependence. You can look at the BKT physics from this type of plots. You get the same TBKT. As I mentioned, it's an electrically tunable superconductor. This is at resistivity versus temperature and filling factor. You have the superconducting domes at -2, -delta, -2 plus delta. Delta is the extra doping. For electrons, you also have these domes, okay? The system in a magnetic field, okay, the superconductivity gets suppressed. If you are at optimal doping, where the system is uniformly superconducting, you just suppress it by a perpendicular magnetic field, initially fast on a 100 millitesla scale, and then it has this long tail going up to about half a Tesla. If you go to the edge of the superconducting dome, where the system breaks into, due to disorder, into superconducting islands, then you can find Fraunhofer-like interference patterns, which tells you that there is Josephson phase coherence through the system. This firmly establishes that this is a superconductor. Now, let me tell you a bit more about the system. So the system is very highly tunable, okay? So this is a plot of the resistivity versus filling factors versus density, and now versus displacement field on this vertical axis versus D, okay? Now, because this is a complex phase diagram, let me guide you a little bit through it, okay? First of all, the light blue regions are regions where the system is superconducting, okay? The resistive features are yellow, okay? Regions where the system is highly resistive are in yellow, okay? Now, in this phase diagram, you can see that there is a certain degree of symmetry. First of all, there's symmetry between the top half and the bottom half, okay? You can see these branches here are also here at the bottom, okay? So there is a certain degree of symmetry between the bottom half and the top half. That means that the system is symmetric in displacement field, okay? Which tells you that the twist angles between, indeed, the middle layer and the outer layers are indeed symmetric. Then there is, depending how you look at it, symmetry or asymmetry between the left and the right, okay, with respect to charge neutrality. There is certainly some degree of symmetry, okay? You can see that superconductivity occurs mostly between filling factors -2 and -3, and between +2 and +3. And you have these sort of branches here at high displacement field, where superconductivity occurs between 1 and 2 and -1 and -2, which have certain symmetry. But at the same time, there are also asymmetric features, okay? For example, these resistive features are much more prominent here than here, okay? So that's asymmetric, okay? And superconductivity overall is stronger here than here, okay? Now, because this diagram is quite complex, we can try to find, measure other properties, not just resistivity and superconductivity, and see if we can correlate them with these features, okay? So in particular, the thing that I'm going to show you is the normalized Hall density, okay? The normalized Hall density is the equivalent of the filling factor for the regular charge density. So it's 4 times the Hall density divided by the superlattice density, these 4 electrons, 4 holes per more unit cell that I mentioned earlier, okay? Now, the Hall density is 1 over, is proportional to 1 over the Hall resistance, okay? So that's important to take into account. So this is the normalized Hall density, okay? As a function of, again, displacement filling factor and displacement field, okay? And as you can see, it's also a relatively complex phase diagram. Now, to 0th order, all of the features, most of the features that you see in this phase diagram can be associated or attributed to one of the following three features, okay? One is a gap/Dirac point, okay? Now, when you reach a gap, a Dirac point, your density of carriers goes to 0. So your whole density, which is telling you the density of free carriers, goes to 0, okay? So features where your normalized Hall density goes from, let's say, dark blue, which means negative high, to negative low, okay, then to 0, and then to slightly positive, and then to highly positive, okay, those features correspond to gap or Dirac points. For example, you can see that at charge neutrality, where you have a Dirac point, okay? You can see that as we go from dark blue to lighter blue, then to white, to red, light red, and then darker red, okay? That corresponds to your normalized Hall density crossing as a function of density, a gap or a Dirac point. Now, you can also have these resets, okay, where your normalized Hall density, grows and then experiences a drop close to 0 and then continues growing without changing sign, okay? These resets correspond to those cascades of phase transitions that I mentioned earlier in magic angle bilayer graphene, okay? And you can see this behavior can be in red or in blue. For example, let me show you one in blue here. So you see you have lighter blue, which becomes darker blue, which then goes to white, okay, close to 0, which then becomes lighter blue and then darker blue, okay? So that corresponds to a reset type of behavior. You can see similar resets also here and in other places, okay? And then the last feature corresponds to von Hoff singularity. The normalized Hall density grows and then abruptly flips sign, okay, and then goes towards 0, okay? At a von Hoff singularity, your RXY, your Hall voltage, goes smoothly through 0, okay, which means 1 over your Hall voltage, so the Hall density diverges, okay? And that's something that you can see, for example, here, okay? Here you go from light blue to darker blue, then it flips sign to dark red, and then goes to light red, okay? So you see this type of behavior there, and that is seen in many other places, okay? So now we have these two phase diagrams, okay, in terms of Hall density, in terms of resistivity, and we can see what features here correspond to what features on the other, okay? Now, because superimposing them directly color-wise would be very messy, let me just do the following. This is, and I want to pay special attention to the superconducting boundaries. This is the phase diagram as a function of density and filling factor. These blue regions are regions where superconductivity exists. In the darker blue regions, superconductivity is very strong. In the lighter blue regions, it's weak superconductivity, but still there, okay? And now I'm going to put on top here schematic lines showing the places where we have these three different behaviors in the normalized Hall density. So, regions where we have this gap Dirac type of transition behavior are shown here in red. Regions where we have reset type of behavior and shown here in yellow, orange. Regions where we have von Hoff singularity type of transition behavior are shown in dark blue lines, okay? As you can see, something very interesting now, a very interesting thing emerges, okay? At 0 displacement field or at small displacement field, superconductivity is mostly bounded by resets between 2 and 3, between filling factors 2 and 3, -2 and -3, okay? But then at high displacement fields, the superconductivity is bounded now by von Hoff singularities or gap Dirac regions, okay, for the most part. So let me show you again this data, and I want to look at across this von Hoff singularity, okay, what's going on, okay? So if I plot the resistivity, as a function of filling factor across there, okay, what you can see is that the system is, superconducting between -2 and -3, and then at -3, sorry, it comes out of the superconducting state, okay? So I can measure BKT transition the critical temperature as a function of filling factor, and of course, it reflects what we know from the resistivity. We have a high BKT critical temperature, and it goes down, and of course, the moment the system comes out of the superconducting state, the critical temperature reaches 0. Okay. Now, I can do now measurements of the effective mass of the charge carriers in the system. Okay, by doing the temperature dependence of quantum oscillations in the system, you can extract the effective mass, and I can measure that effective mass as a function of filling factor. The effective mass in a solid state system is proportional to the density of states. Okay, so when I measure the effective mass as a function of filling factor, the exact same trace. Okay, what I see is that there is this divergence, here at this point. That divergence corresponds to the Van Hoff singularity. Okay, Van Hoff singularity gives you a divergence in the density of states. Okay, and the interesting thing, as you can see, is that the superconducting critical temperature, okay, becomes 0 at the Van Hoff singularity. Okay, now this is very much unlike weak coupling BCS superconductivity. Okay, in BCS superconductivity, there's a formula that gives you what is the critical temperature as a function of the density of states, and it's exponential in the density of states. Okay, it's exponential in -1 over the density of states. When you have high density of states, you expect your critical temperature to grow and to become very high. However, in this system, as we change the filling factor, as the density of states increases, the critical temperature decreases rather than increase. And moreover, at the Van Hoff singularity, the critical temperature becomes 0. Superconductivity ends at the Van Hoff singularity instead of being maximum and strongest at the Van Hoff singularity. Okay, so this is something which is very unusual. Now, let me tell you about strong coupling superconductivity. So we can measure this TBKT in the entire parameter space versus filling factor and displacement field. Okay, so this is a 3D plot of that TBKT as a function of filling factor and displacement field. Let me project it here on this plane. Okay, now you can, this is a little bit complex. So I'm going to show you cuts at optimal electric field as a function of density, and then at optimal density as a function of electric field, okay, displacement field. So this is a TBKT as a function of filling factor at optimal displacement field. As you can see, we have this big dome for holes, a smaller dome for electrons, okay? I can now, along the same trace, okay, I can measure also my superconducting coherence length, the Ginzburg-Landau superconducting coherence length, by doing magnetic field measurements, okay? And this is what it looks like. As you can see, the superconducting coherence length in the system is extremely short, okay? In fact, if I plot here what is the average interparticle distance for the system, this is this red trace. And as you can see, near optimal doping, the superconducting coherence length is bounded by the average interparticle distance, okay? I should remind you that these moiré quantum systems, the superconductors, are the lowest charge density superconductors that exist in the world by far, by orders of magnitude, because of the large moiré unit cell lattice, okay? Now we can do the same thing at optimal density as a function of displacement field, okay? This TBKT, this is the superconducting coherence length, and this is the average interparticle density at optimal density, okay? So at optimal doping, the Cooper pair size is of the same order or smaller than the average interparticle distance, okay? So that's something that immediately reminds us of what happens, in the BCS to BEC crossover, okay? This is a plot from, Mohit Randeria's review. This is a plot which is typically shown in the context of cold atom systems, okay? Where, with the Feshbach resonance, you can tune your interaction strength, and you can go all the way from the BCS limit, where your Cooper pairs are like, electrons in a Cooper pair are like at the end of a spaghetti, but you have lots of spaghetti, in your pasta plate, okay? You can tune this all the way to the BEC regime, okay, where your molecules, your bosons are tightly coupled and bound, and the average interparticle distance between your molecular, between your bosons, between your molecules is very large compared to the molecule size. And in this BCS to BC crossover, the Cooper pair size is of the same order as the interparticle distance, okay? In 3D, the critical temperature versus the Fermi temperature is bounded, 0.22. In 2 dimensions, it is the BKT temperature over TF, which is bounded, and is bounded at 0.125, and it's reached at the BCS-BEC crossover, okay? So, because we can measure our Fermi temperature and our TVKT, okay? By measuring, for example, we have the Fermi temperature, we don't have the density, and we can measure the effective mass. So we can plot TVKT over TF as a function of density at optimal electric field. We can do the same thing at optimal density as a function of displacement field, okay? And this is 0.125, okay? So TVKT over TF in the system reaches values in excess of 0.1, with the maximum actually at about 0.125, okay? So this system is close to the BEC-BCS crossover, okay? Now, the fact that it reaches exactly 0.125, I wouldn't make too big a deal out of it. That theory that I showed you is for cold atoms, where the boson mass is twice the mass of the fermionic atoms that make the boson. For electrons, that is not necessarily the case, okay? But still, this is the highest values that have been reached in any solid state system. So usually, we characterize how strong superconductors are by what's the ratio between the critical temperature and the Fermi temperature, okay? Conventional superconductors are typically in this region, gigantic Fermi temperatures, but very modest critical temperatures. This is the line for BCS crossover in 3D. Okay, in this purple band, you have pretty much all of the unconventional superconductors. This is the line for TVKT, okay, for BCS-BEC crossover. And magic angle twisted bilayer graphene, depending on whether you take TVKT or critical temperature at 50%, is in this region. Magic angle trilayer graphene is here, okay? It's the strongest coupled superconductor that exists in the world, okay? Recently, another system has appeared which has similar coupling strength, okay? Now, let me tell you about an unexpected surprise that happened, okay? So, when we measure magic angle twisted trilayer graphene in a perpendicular magnetic field, we see that superconductivity is suppressed, due to orbital effects. And that happens well below 1 Tesla perpendicular magnetic field, okay? Now, because this system is a 2-dimensional superconductor, if you apply an in-plane magnetic field, you don't have the typical orbital effect, you don't create vortices, with an in-plane magnetic field. So it's interesting to see what's limiting the superconductivity with an in-plane magnetic field, okay? Now, usually, in conventional superconductors, okay, your Cooper pairs have a spin singlet configuration, right? And the binding energy in BCS theory, okay, is given by your gap, your superconducting gap, which is 1.76 times kVTC, okay? Now, if you apply a Zeeman magnetic field, okay, the Zeeman effect breaks apart Cooper pairs, okay? Because you spin up and spin down electrons. The Zeeman splitting is, equal to G mu BB, okay? So there is a limit called the Pauli limit, or the paramagnetic limit on the order Chandrasekhar-Klockstone limits, where essentially once your Zeeman splitting is equal to your binding energy of your Cooper pairs, you just break your Cooper pairs apart, okay? So that tells you that for a conventional superconductor, okay, you expect to kill superconductivity due to Zeeman effects at your critical field is expected to be about 1.86 times your critical temperature, okay? So for a critical temperature of 1 Kelvin, you expect to have your critical Pauli field to be 1.86 Tesla. That's for BCS spin singlet superconductors, okay? So let me show you what happens in trilayer graphene. So, we warm up our sample, we rotate it, and we cool it down in a system where we can apply an in-plane magnetic field. These are the data at 0 magnetic field, parallel, very similar to before. I think you recognize it from earlier. Now, you apply, here at optimal doping and optimal electric field, our critical temperature was about 2.7 Kelvin in this cool down. that means that the Pauli limit should be about 5 Tesla. By 5 Tesla, superconductivity will be completely gone, okay? Well, we measure at 10 Tesla parallel field, our superconductivity is still present in the region of optimal doping, okay, over a broad displacement field, okay? In fact, you know, I can show you the VI traces so that you can see that this is indeed robust superconductivity all the way to 10 Tesla and beyond, okay? You can look at these, you know, zoom-ins of this phase diagram in filling factor and displacement field at different parallel magnetic fields, and you see that superconductivity gets suppressed gradually, but it still persists at fields beyond 10 Tesla. Now, in order to look at how much, you know, are we violating the Pauli limit, we need to do temperature dependence measurements. So these are at optimal electric field, measurements of the resistivity versus filling factor and temperature, okay? At 0 parallel field, 2 Tesla, 4, 6, 8, 10 Tesla. So you can see that there is still a well-defined superconducting dome at even at 10 Tesla, okay? We can extract the critical temperature, okay? And in particular, we can plot this resistivity versus temperature and be parallel, okay? So this is one of these cuts for a given, you know, continuously as a function of parallel field for a given filling factor, okay, for a given density, okay? And you can see that, you know, we can plot here equal resistance contours, you know, 10%, 20%, 30% of the normal state resistance. The same thing happens for 50% or for BKT, okay, for the transition to 0, exactly, okay? We can look at the following. These contours happen to be quadratic in magnetic field, okay? And B Pauli, okay, is 1.86 times TC. So we can, you know, whichever threshold we want to take for TC, we can take it, and we can find what is the Pauli limit. And the Pauli limits are here for these different thresholds, okay? Which means that we're violating the Pauli limit by over a factor of 3 at this particular density, okay? Now, there are different mechanisms by which, you know, the Pauli limit can be violated. For example, a strong spin-orbit coupling. You know, the monolayer ion, the selenide, has very strong spin-orbit coupling and violates the Pauli limit. However, graphene has a very small spin-orbit coupling, okay? It would have to be the spin-orbit coupling in trilayer graphene 30 times larger to begin to account for the violation that we see. Okay? Another possibility is FFLO states, finite momentum pairing states, okay? Those can give you an enhancement of maybe 20, 40% at low temperatures, but we see our enhancements of a factor of 3 and already starting from TC. So this again is not possible. Another possibility is that because we're in strong coupling regime, we have a pseudo gap where the amplitude pairing has nothing to do with TC. TC is determined by the superfluid density or the phase stiffness, okay? But we see, however, that this violation of the Pauli limit is present everywhere in the entire superconducting dome, even though the coupling strength can vary by over an order of magnitude, okay? So this means that it is very unlikely that any of those mechanisms explains our data, and therefore it's very unlikely that our Cooper pairs have spin singlets, are spin singlets. Now, in the last couple of minutes, I want to tell you about another behavior that we see, which is very anomalous. The data that I showed you were at optimal electric field and optimal density. If we measure at smaller displacement fields, what we see is re-entrant superconductivity at high magnetic field, okay? So this is showing only data in the high field region. You see that you kill superconductivity, and then once you've killed it, then it reappears at higher magnetic field, okay? That's something that, you know, we call superconducting 1 and superconducting 2 regions. You can do this also in the critical current measurements, and this is extremely strange, okay? It is very rare for superconductivity to reappear at high fields. There are a few systems where this happens, okay, and these are typically ferromagnetic superconductors or spin triplet superconductors. We don't have ferromagnetism in our system, okay, that we have been able to detect in the region where superconductivity is. So the most likely option is that our system has a spin triplet superconductivity. Okay? We can check the phase boundaries between the superconducting 1 and superconducting 2 regions, okay? And this occurs over extended regions in displacement field and density. And right now, the only possibility that we and our theory colleagues have thought of is that this is spin triplet superconductivity. So with this, I just want to spend 1 minute telling you about some of the outlook. I'm running out of time, so I won't tell you much about the summary of this magic and twisted trilayer graphene. The outlook is that we can probably make 4 layers, 5 layers, new moiré, robust superconductors, okay? Where who knows what the spatial or the parameter is going to be in those systems. We can make, almost all phases of condensed matter now in these twisted systems, okay, with these moiré correlated lattices, from correlating insulated superconductivity, topological phases, even ferroelectricity. This is with simple systems. You can also make all of this with more complicated systems that you can now twist among themselves and give rise to even more complex and richer type of behavior, okay? So 2 examples are twisting cuprates or twisting magnets, okay? Theoretically, people are already predicting very interesting behavior. And the last slide is that this all goes also beyond condensed matter systems. People are doing these things with cold atoms, including work done at ICFO and also at Munich, okay? People are doing this with phonons and with classical mechanical systems, more twisted phononics. People are doing this thing with photons, okay? This is work from ICFO, actually. So this is a very big field, that is just emerging and that, it goes beyond condensed matter physics. So with this, I want to acknowledge my collaborators, and I hope we soon can all go back together to having this type of events. And I want to thank you for your attention.
So thank you very much, Pablo, for your very nice talk. That's some very impressive results. So